for the invitation, for giving me this opportunity. So today I would like to talk about some more recent work, which is somehow work in progress with James McKernan. Somehow, one of the reasons why I chose to talk about this is because it fits very well with what both James and Chen-Yang have been talking about over the last few days. So I'm going to start with a very slow introduction. First of all, I would like to remind the criterion that James mentioned yesterday, although probably he will mention it as well, for local, it's a local criterion for toroidal pairs. But before doing that, let me fix the setup. So I'm going to talk about singularities, isolated singularities, exactly like in Chen-Yang's talk somehow, and at least Chen-Yang's talks yesterday. And so I'm going to assume that we are on a germ, algebraic germ, analytic germ, around at a point P x in x of dimension n. Again, everything is over the complex numbers. And for the sake of this lecture, I will always assume that x is q factorial. And KLT. So, on the other hand, we will look at pairs. So we will often look at pairs, and our pairs will have singularities which are usually a worse low canonical. Okay, so in particular, I'd like to recall yesterday's result. I mean, if x theta is a low canonical pair, sorry, maybe I should say so first of all, I'm assuming that since we are working on a germ of a singularity, all the psi, of course, contain the point P. So maybe I should say fix the indices. Okay, then the easy fact is that the sum of the I, it's always less or equal than n. But somehow, if the quality holds, or something a bit weaker than the quality holds, then the pair holds. Then the pair is toroidal. So if the sum is exactly equal to n, then x theta is toroidal. I mean, like we saw yesterday. There are weaker assumptions that allow us to say something like that. But for today, I think that's all we need. Okay. So surely this is a very simple criterion to check if something behaves very much like a toric variety around the point P. So let's see some very simple example of this. Excuse me?
I mean,
did I get it?
You had like A2 and 4 lines. Or 3 lines even, through a point.
3 lines in a point with coefficient equal to 1?
2/3.
2 curves.
2/3.
2/3, okay. Oh, I see, okay. Okay, so let's see. Okay, let me just say x is toroidal, and then at least 2 of the components are, so yeah. How about that? Sorry, yeah. Okay, so let me start with an example. Let's suppose that we are in dimension 2. So in this case, of course, KLT singularities just correspond to finite quotient singularities. So in a sense, they're very well understood in terms of looking at the quotient of a finite group over acting on C2. Nevertheless, we could look at them from a different point of view, and again, they're classified. We can look at the minimal resolution. And we can look at the graph of the exception locus of F. So again, everything is around the point P. So we just look what happened at the inverse image of F of P through F. So this is just a union of curves, and characterizing KLT singularity means characterizing the graph defined by these curves here. So in particular, this is a very, very simple example of a dual complex that comes out of it. So we know that there are very few possibilities for the dual graph associated with this. So for instance, one possibility is the AM singularity. Which means that the dual graph associated, or dual complex, it's a union, it's just a path of rational curves of negative self-intersection. So all it means, again, if you look, this is the dual picture. All it means is that this is just nothing but something like this in terms of the exceptional graph. Okay, so what I would like to show is very simple, is to use this criterion to show that this is actually a toric singularity, meaning that it's really, of course there are many, many other ways to look at it, but in order to understand this criterion, this is really coming from, it's a very, very simple of the example we saw before. So all we do in the rest, so this is on Y, of course, which is mapping on the point P, which is our singular point. So what we do is to take, and of course we can do that, two curves, which I'm going to call C'1 and C'2, which meet the two tails of this path. In other words, we meet the two curves at the extreme, which corresponds to A1 and AM. Okay, and they meet transversally, meaning that Y is a smooth variety, so I can definitely find such a curve. Okay, and then we take the image of these two curves on X. Sorry, Y goes to X, and of course, each EI goes to P. But now we look at the image of these two curves, which of course are going to touch each other because all these curves have been contracted, so they will both of them will pass through the point P. So if you look at the image, it will be nothing like this. So I'm going to call C1 and C2 the image of C'1 and C'2. And of course, the point of intersection is nothing but the point P. Okay, but then in this case, it's very easy to check that just by easy linear algebra problem, that if we take the pair defined by C1 and C2, maybe I'm using F as a notation of the map, and I take the pullback of this guy, what I get is Ky plus, of course, I'm going to get C'1 plus C'2, which are the strict transform of C1, C2 by definition, and then all the exception divised with coefficient equal to 1. So in particular, since everything here is simple normal crossing, this is a log resolution of this pair. And it's actually also the DLT modification, it turns out to be. But anyway, what is important here is that all the coefficients are less than 1. So the pair X C1 plus C2, it's definitely log canonical. Of course, the point P passes to the curve C1, C2, and of course, this pair satisfies this property because 1 plus 1 is equal to the dimension of the variety X. So in particular, X is toroidal. In this case, we can really show that even the pair C1 and C2 is toroidal, but okay, I'm not going to go into that. So let's look at this different example of surface singularity, which is again is the second large family of KLT singularity in dimension 2, which is given by dm singularities. So in this case, the picture is very similar to this, but we have a fork. So it's something like the dual graph associated to the dm singularity is given by this picture, where these are the curve E0. I mean, just as a meta notation, I denoted by 0 and minus 1. Then this is the curve E1, and I suppose here it's minus 1 or minus 2. Okay, so in order for this to be a KLT singularity, we need to add this extra assumption that the self-intersection of the first two curves is equal to minus 2. This is again an easy calculation, as otherwise it wouldn't be KLT. Every other curve, exactly like in the case of AM singularity, can be of arbitrary self-intersection, of course negative. Okay, so what I want to show is that this is not a toroidal singularity. So somehow we live in a different world than from this one here. Okay, so again, this was shown in one of the lectures before by James. It proved, I mean, we know that there is, if X is toroidal, then there exists, actually if you take the invariant divisor at the point P, so there exists the reduced divisor, so in particular greater or equal to 0, such that XD is canonical, it's all canonical, and actually Kx plus D is Cartier. It's actually linear equivalent to 0, but since we are on germ of a singularity, all it means is that it's Cartier. So this, of course, is a very strong assumption because, and of course it's true here. In this case, Kx plus C1 plus C2 would be Cartier. But for any toric variety, these things would happen. Okay, so now, exactly like before, let's take the pullback of this pair. So this will be equal to, as usual, Ky plus the strict transform of D. Plus some divisor which are contained, which are supporting the exceptional locus of F. So it would be something like maybe Bi, Ei. So one thing that we notice is that Bi must be integers. And the reason is because Kx plus D must be Cartier, otherwise this is not true. But also, without D, all this Bi will be equal to 0, because it's a canonical, this is an example of a canonical singularity. So since we add something which passed through the point P, we have that Bi must be greater than 0. All of them. But on the other hand, it's log canonical. We're assuming that it's log canonical. So it must be less or equal than 1. So clearly, if you join all these together, it must be equal to 1 for all I. Okay, but now what we got is that actually the pullback of Kx plus D is equal to this plus the sum of the I. And we'll see, we'll find a contradiction by just, and this is a standard method, by just intersecting with E1. So if we multiply by E1 on both sides, what do we get? Okay, on one side we get easily 0 by projection formula. We have pullback of something times exception divisor must be equal to 0. On the other hand, on this side of the picture, what we get is, okay, maybe I shouldn't have written greater or equal, but what we get is K1, sorry, the degree of K1. Why is that? Because K1 times E1 times E1 on a smooth variety is just equal to the canonical, I mean, restricted to E1, it would be just the canonical divisor of E1, plus E0 plus E minus 1 and E2, which are the three curves which intersect E1, plus something which is given by the intersection of dy times E1, which is definitely a non-negative number. So it's easy to check that we get this formula by just purely intersecting these two divisors. Okay, but clearly E1 it's P1, so we get a -2 here. And by the picture, it's very clear that this is greater or equal than 3. Actually, it's equal to 3, sorry. So we get this number here on the right-hand side is greater or equal to 1. So this is a contradiction, which implies that X cannot be toroidal. So somehow...
What case must use cut here?
No, I'm assuming it's toroidal. So there exists...
So what's your definition of toroidal?
So locally at the point P, it's isomorphic to, analytically isomorphic to toroid variety. So if you take the invariant divisor, must be, this must be true.
Okay,
so it's a one complement, if you want.
It's a bit strange, Paolo, because I mean, you could see immediately, right, that it's not toric.
I mean, I know, you can see from many other reasons that it's not toric.
Okay.
But I wanted to just check from, from this criteria point of view that is not toric. Okay, so somehow now the question is how different these two pictures are. Namely, how to go from, okay, so is it possible to find some kind of, like written here, some kind of toroidal resolution which makes this singularity closer to be toroidal? Now, of course, if I resolve the singularity, everything is toroidal. I mean, smooth or toroidal. But like was mentioned a few days ago, we want to find some kind of modification which extract very few divisors. So I'm still in this context here. I'm still talking about the n singularities or the m singularities. So we know that given the minimal resolution of a surface and given any curve or any subset of the exceptional locus of f, we can find a decomposition of this into a factorization of this into two maps. So there exists such a diagram such that the exceptional locus of y1 is equal to the curve E1. Sorry, exceptional locus y1 over x, so let me call it f1, is equal to E1. Okay, so in other words, we can find, we can factorize this and collapse all the curve, contract all the curve except E1. And this morphism will contract E1 only. So what happened to this picture here? I'm going to draw something similar to this. So on Y, we have such a picture, which is the graph, which is the set of all the exceptional locus that appear. Now I'm contracting all the curves except this curve here, E1. So what I get is three singular points, which corresponds to the image of E0, so let's call it P0, the image of E minus 1, which I'll call P minus 1, and also the image of all these curves, which are called P1. So now the point is that all these 3 points are exactly the same as the singularity we had before. So this is actually A1 singularity. And same as this, because the exceptional locus is nothing but one curve. So it belongs to a path, it corresponds to a path of length 1. And this one here, it's a, let me get it right, n minus 2 singularity. Okay, so around any of these 3 points, we have that, so y1 is toroidal at the point p0, p minus 1, p1. Okay, why? Because it corresponds exactly the same picture as this with 3 different singularities. Okay, so in a sense, although we didn't resolve the singularity, y1 is not a resolution of singularities, but is somehow better, it has better singularities than x itself. And now, another comment is that the only thing we did was to extract one divisor. Okay, from y1 to x, so the relative Picard number between y1 and x is just equal to 1. So in a sense, it's not a resolution singularity, but we somehow, it behaves well with the philosophy that James was talking about, that the toric varieties are a bit everywhere. Of course, this is not the end of the story for Keltis surfaces singularities. There are 3 more families of singularities, but the picture is exactly the same as DM singularities. It's even easier because they are bounded in family. So the same claim happens for all the Keltis singularity in dimension 2. So now the question is, how can we try to generalize this picture in general? So what happened in higher dimension? Okay, we try to find some sort of cheap way to resolve singularities where we relax the meaning of resolution singularities. We don't want the variety above to be smooth, but we want something like toroidal. Okay, we are still, far away from this, but first of all, we do need to have some kind of, I need to mention some kind of way to generalize this, because clearly this picture is much simpler because we're always allowed to factorize graphs resolution like this one. So let me try, before we start talking about toroidal modification, I need to talk a bit about log discrepancies. So we're already defined 2 times. So I'm not going to give the definition, but just to remind you, we assume that x delta is a log canonical pair, is a divisorial evaluation on x. Then the log discrepancy, and here it's the word log means that we start from 0, it's always greater or equal than 0. Because it's a log canonical pair. Also, so it's the coefficient of E1 minus the coefficient of E of the difference of kx plus delta and proper image on y, on any resolution of x. Okay, so one fact that somehow corresponds to this picture here is that if E1, EM are valuation, divisorial evaluation such that the log discrepancy of x delta along EI is less than 1. So again, we're in the interval 0, 1. Then we can do exactly what we did before. We can extract, we can go from y1 to x, extract only this divisor here. So in other words, there exists, maybe let me write it here. from y to x, which is not a like solution, but it's something that extracts only the device we want to extract. In other words, there exists f such that the exception locus of f is exactly equal to the union of the EI, where these are the devices we wanted to extract. So this is not quite a factorization of the resolution, because there could be flops in the middle. But it's exactly what Chenang was talking about yesterday, in the sense that it's obtained by running some mere model program over X. So somehow it's a useful picture, because we are allowed to do exactly what we were allowed to do here. We were allowed to extract what seems to be useful to extract. So this is the fact that will play a major role for us. Another fact, another definition before I continue. It's a low-canonical center. So if W to X is a proper branch morphism, which contract a divisor E of log discrepancy 0, then the image of E, in other words, the center of E on X, is called the low-canonical center of X delta. In the minimum model program, this plays a very important role, because somehow the places, for instance, where we can lift, I mean, we can apply a junction, or we can lift section from. So somehow, okay, now we can give some definition. I mean, we can go back to toroidal modification. Okay, sorry, before I talk about toroidal modification, we start with something which is KLT. But now we end up with something which is, I mean, we seem to like things which have, exactly like here, all these EI that we saw before were the image were low-canonical centers of a pair XD. So we want, how do low-canonical centers appear if we start with something which is KLT? So I'm going to talk about, one of the essential tools in this picture is the complements. So what is a complement? Okay, this is, first of all, I should say this is due to Shukurov. Let's suppose that, sorry, I'm a bit, X delta is a KLT pair. Then, okay, there are various ways to look at it, but I'm going to define what is usually called the effective complement. Then an M complement, sorry, there are too many, R complement of X delta is a pair X theta, such that, first of all, theta is greater or equal than delta. Okay, this is easy, of course. Since we are working on something called factorial, even if you want Kx plus theta, it's always easy to get. The second property is that X theta is low canonical, but not KLT. And again, this is easy because we can always take any divisor and, exactly like what we did the last lecture, increase the coefficient in such a way that this is verified. Although there are singularities now, but these two properties are always very, very easy to obtain. What is not easy to obtain is that M Kx plus theta is Cartier. Which is very, very similar to what that's the reason why I chose this way, although maybe it's not the cheapest way, which is, in this case, this would have been a one complement. Sorry? R, thanks. R times kx plus theta is Cartier, yes. So in this case, it would have been a one complement. So any toric variety, if x is toric, then, or toroidal, sorry, then there exists always a one complement around the point P. So the conjecture is that if you assume, for instance, delta equal to 0, then there exists a bounded R, which depends only on, where the boundary depends only on the dimension of the variety x, which for each variety x, it will there will be a R complement, where again R is bounded by some constant which only depends on the dimension of the variety we are considering. So what does this say? This says pretty much that, okay, even if we start from something which is not log canonical, but it's guilty, I mean, which is stronger than being log canonical, is guilty, we can, without losing too much, we can always create log canonical centers. So we can always create valuation for which this property is satisfied. So in particular, in dimension 3, or 2 of course, there exists R less or equal than some number which depends only on the dimension of x, sorry, n, such that, sorry, I should say, for any x of dimension n, where n is less or equal than t, there exists R, such that x admits an R complement. So, and in this lecture, we always work in dimension 3 or less. Okay, so I can finally define what is a toroidal modification. So what is this? So it's exactly the same as what we're trying to do here for surfaces. Something that is not quite a resolution singularities, but is the closest we can get in a cheap way. In other words, it's the closest we can get by extracting very few divisors, at least we believe. Okay, so let's suppose that x theta now is a log canonical pair. Let's suppose that y to x is a proper Brownian map. Then f is called the toroidal modification. If the following is true. So first of all, we only extract, sorry, toroidal modification for x theta, of course. So the first property that we want is that we only extract divisors of log canonical, or log discrepancy equal to 0. So in other words, for any E, exception for F, the log discrepancy of E, of x theta with respect to E is equal to 0. Okay, this is, again, is nothing much. We can always do that. I mean, we can always extract such divisor. But sorry, I need to split into two. Well, maybe I can write it here. And then, so what does it mean? It means that if you look at, in particular, this means that, so maybe I should put in parentheses, if you look at kx plus delta, the pullback of kx plus theta, this is equal to ky plus theta y, where theta y is usually the strict transform of theta on y, plus some sum, finite sum of exception divisors of log discrepancy 0. So all the coefficient here will be equal to 1. So where E1, EM is exactly the set of all the exception divisors of F. So I guess I don't have any space here. So again, I could take the identity. So far I didn't say anything about toroidal modification. I need the most important property. So the second property, which is again the most important one, which characterizes toroidal modification, is that the pair y theta y plus the sum of vi is toroidal at the general point of any low-canonical center, of any of its low-canonical centers. So again, this is a technical assumption, but what it means is that those points where we want to find, we want to resolve singularities, are as nice as toroidal historic varieties. So, of course, we would like to live without this assumption, but that makes things much more difficult from our point of view. But I should say, in this particular case, of course, this is an example of a toroidal modification. I mean, this one here, it's a toroidal modification. So another example, which is even easier, is what Chen Yang talked about yesterday. If y2x is a DLT blow up, or DLT modification, of the pair x theta, then f is a toroidal modification. So we definitely know the existence of toroidal modification. The question is, why do we need something? Why we're not happy with this? Well, let's go back to the example that we had at the very beginning. Let's go back to the AM singularity. So again, I'm going to assume that x is equal to the singularity we start at the beginning, AM, and we take theta to be exactly the same pair that we took at the beginning, C1 plus C2. So it just means that we had two curves passing to the point P in such a way that if we take the resolution, the minimal resolution was given by this graph here. Now, in this particular example, this is the minimal resolution is exactly the toroidal modification. Sorry, it's the DLT modification. On the other hand, we started from something which was already toroidal, because this is already toroidal. So we didn't need to take a toroidal modification. Of course, it's a DLT modification, and it's the cheapest DLT modification, meaning that it's the unique DLT modification. We cannot do anything better than this. So this one.
No, you can always upstairs. You can always blow up.
Oh, you can take more. Sure. But this is the cheapest one, in a sense. The one with the smallest Pican number, relative Pican number. So, in a sense, if you want to go to a DLT modification, we need to extract at least. We need to take a morphism which contracts at least m divisor. So the exception locus, rho of y over x, in this case is equal to m. So we have arbitrary long sequence of divisors to extract depending on this m here. So somehow we started from something toroid, and to get something DLT, we need to extract many divisors, and it's not possible to bound it. So what we're looking for is something somehow cheaper, in the sense that which extract fewer divisors. Okay, so I should say finally what is the theorem. So let's go back to dimension 3. So what we can do is exactly the equivalent of what happens for surfaces, although of course the bound becomes a bit bigger. So let's suppose that n is equal to 3. And let's suppose then there exists a constant, which is actually very easy to compute, although we never really computed. Then there exists m, positive integer, such that if x theta is a log canonical pair, then there exists a toroidal modification for y to x such that the Picard number of this resolution is less than this constant here. Okay, so again, in this example, f would have been the identity, because this is toroidal from the very beginning, so there's nothing to resolve. And of course, if we choose f to be the minimal solution, we wouldn't have satisfied this property. In the example of the m singularity, then it would have been exactly the picture that we had at the very beginning. It would be the extraction of the E1 curve. I should say that in this picture, we always assume, exactly like at the beginning, that x is QLT and is Q factorial. So let me give a very brief idea on how to prove this. So first of all, what I'm going to do is to use the same criterion that we had at the very beginning for toroidal pairs. So what is the hope? The hope is to find, or the plan is to find f, like here, any function, any proper bidirectional morphism f y to x, such that at any log canonical center, so for instance, any zero-dimensional log canonical center, the inequality we had at the beginning is satisfied. So we have a pair y gamma. So let's say f is come from y to x as usual, and gamma is such that, as usual, ky plus gamma is the pullback of kx plus delta. Okay, maybe I should say, sorry, at any zero-dimensional log canonical center Q of y gamma, we have that gamma is of the form BI-SI, where the sum of BI is equal to 3. If we can do that, then we're done, because again, we can use the criterion that we had at the very beginning, and we can conclude that what we had before. Actually, I'm a bit sloppy. I should say that maybe we want a little bit more in order to get that the whole pair is toroidal. What we want, in this way we get y is toroidal. But maybe what we really want is that, even better, what we want is that gamma is of the form S1 plus S2 S3 at the point P, where of course the point Q, where of course Q belongs to the point, Q belongs to S1, S2, S3. Okay, so let me draw a picture to make things clear. But what we want is that the best of the criterion that we want. In other words, we want one complement on the variety y which satisfy the property that this is true. Namely, the graph would be like this. Oops, sorry. So at the point Q, the picture will be exactly like the best we can hope. S1, S2, S3. So this will be gamma. And at this point Q, which we're considering on Y, it will be toroidal by the criterion that we had before. So in other words, what we want is that we want to force things in such a way that the number of components of coefficient 1 passing through Q is as high as possible. In this case, 3. Okay, so how do we do? Well, first of all, let me give a very naive approach, which doesn't quite work, but somehow it gave us the beginning, motivation to start this program. So suppose that we take, so let's suppose that G from W to X is a DLT modification. So what we have is that, exactly like Chen-Yang was telling us, is that we have the dual complex associated to, so let D E to be the corresponding to complex. So which looks like something like this. Well, there is some fantasy and so on. Well, I'm missing something, of course. Okay. So it should be Simplicio, but of course this is not Simplicio, but something like that. Okay. So first of all, what appears in this picture is that what is possible, Chen-Yang said, this picture, it's always, we also always obtain something which is contractible, because we are working on a Q factorial DLT modification of something KLT. So by their result, by the Fernet-Collard and Chu, we already know that this is contractible. With very, very little work, we can prove a little bit more, namely that there are no, it's either of this form, the composition of a planar picture, or it's a chain, or a path, sorry. So there are these two pictures. There is nothing more fancy than that. It's not possible that we have something like, something like this cannot happen. And again, this follows from standard results, which actually Chen-Yang was talking about yesterday. Okay, so that's the first thing that we notice. So what will be the plan? Sorry, let me go back to the picture. The plan will be, this is what we see above on W. But now each of these vertex defines a divisor with log discrepancy equal to 0. So we could take 3 of these guys, E1, E2, E3. Both of them have, all 3 of them have log discrepancy equal to 0 by definition of divisoria of DLT blow up. And we could find F to be a map from Y to X, which extract E1, E2, E3. We know that this map exists. Okay, but the problem, what do we get? We get 3 divisor passing through, 3 divisor, which are exception divisor for F, which should look exactly like this. Because they have coefficient 1, they should intersect along a point and so on. The problem is that, unfortunately, we're never able to make, although this looks very promising in some sense, it looks like the right way to look at things. Things become much more complicated because to go from W to Y, we need to go through flops. And so, exactly like Chen-Yang explained, this picture will be messed up after after one step. So it's very difficult to keep track of this way of proceeding. But somehow, the idea is very simple. We do expect that extracting 3 divisors, we should have something that looks very much like this. Okay, sorry, I'm running out of time. So how do we proceed instead? Well, the way we proceed is actually, again, it's very naive. What we do is this. We work, given a pair y gamma, at each point Q, at each zero-dimensional low-canonical center, we define the constant m to be the number of components of gamma of coefficient 1. And of course passing through the point P, the point Q. Okay, so again, it's exactly what we want to do. The goal is to find y such that m is equal to 3 at each zero-dimensional canonical center. Of course, we need to take care also of higher dimensional canonical center. But in a sense, those are easier because we can always cut through some hyperplanes. So the most difficult one to deal with are the zero-dimensional canonical center. Okay, so the idea is that we want to increase m. So we start from the very beginning. We start from the smallest value of m. If m is equal to 3, then we are OK. Because if m is equal to 3, it's exactly this picture here. So in other words, it's exactly this picture here. So we know that it's going to be toroidal. So let's start from the opposite side. Let's suppose that m is equal to 0. OK, what happens if actually m equal to 0 is the easiest case for, well, at least for threefolds. In general, it has some complication. But for m equal to 0, first of all, I should say in this theorem, if you assume that x delta is KLT, there is nothing to prove, right? Because we can choose f to be the identity and the result will be true. So clearly there exists a point, there exists E. I say at the beginning, x is always Q factorial. Yeah, I say whenever we work with x, x will be always Q factorial. Yeah. Yeah, so if you want, what I say is that x is Q factorial and is KLT. So what I say is that at the beginning, I will never touch this condition. So we know that there exists, since we know that it's not KLT, we know that there exists E of log discrepancy 0. Okay, so what we know is that we can extract this E. So what does it mean? So maybe, sorry, I should call it H. This is the first step of our resolution. From y1 to x, such that the exceptional locus of H is equal to E. Okay, but then what happens? Then I can write ky plus theta y1, which is nothing as usual, the strict transform of theta, plus E equal to H star of kx plus theta. Okay, so what happens here? So clearly now all we care about is what happened along E. So this is E, which maps to point P. So clearly this one will have at least one divisor with coefficient equal to 1, which is exactly this one. So this is y1. So for each point, for each low-canonical center of y1, theta y1 plus E, we have that m is actually, I should say greater or equal than 1. It's actually turned out, since I'm assuming that we start from something with m equal to 0, it will have exactly m equal to 1. Because again, m counts the number of components of coefficient 1. But clearly, E has coefficient 1. Theta 1 maybe is it's going to be fractional by our assumption. So we obtain this almost for free. OK, so now okay, I'm running out of time, so I'm not going to be able to go through all the steps of the proof. But one thing that I would like to say is that by some form of connectedness, the number of local canonical center inside E is bounded. So actually less equal than 3. Because of course, the problem, and this is a problem, I mean, at least as far as I know, it's a problem in higher dimension. We could have arbitrarily many zero-dimensional canonical centers here. So we can assume that E is Fano and so on. But we don't know how many local canonical centers are here. If this is the picture, then we are in trouble. Because, at least for our way of proceeding, we are in trouble. Because we have no idea, I mean, we need to extract one divisor for each of these points. And if we don't know how to bound this number of points, then definitely we're not going to be able to prove something equivalent to what is written here. On the other hand, in dimension 3, this is not going to happen. The number of local canonical centers on E is almost 3. And so clearly we can take one by one, and we can assume that for each of these points m is equal to 1. So I can assume that m is equal to 1. Okay, because again, at most we have 3 points which we need to take care of. We take care of each of these points. Whatever the bound we get for each of these points, we're going to be happy. Okay, so now, I should say, from now on, the proof is not very different from what we're going to say, what we're saying now, just that it becomes, we don't have quite a clear proof. What we have is to distinguish many different cases. So what we do is to look at the singular locus of E and cut through the singular locus of E if it's not normal. Or, I mean, again, the proof proceeds by distinguish several cases. So I definitely don't have time to go through the step. So I think I'm going to stop here. Thanks very much.